In this lecture, we're going to discuss what is probably one of the most vibrant and advancing areas of materials characterization at the moment, and that is the advances that are currently occurring with regards to high resolution transmission forms of electron microscopy. And we'll explicitly cover both standard transmission mode electron microscopy and scanning transmission electron microscopy, which both offer advantages and comparative forms of advantage in materials characterization, and hopefully we'll illustrate some of the differences between these techniques and how they both serve to provide useful information about materials. First off, it's useful to talk about the forms of radiation that we might use to characterize matter and its structure and its properties at the level of atomic resolution. We saw yesterday a number of cases whereby information regarding composition, and in subsequent lectures we'll see also examples of how we can determine information about atomic bonding and structure via the use of X-rays. X-rays are, of course, an electromagnetic wave which have very short wavelengths. The wavelengths being of the order of interatomic distances make it possible for us to use interactions of matter with photons, in this case, as a way of actually determining the atomistic positions and identity of atoms that comprise a solid material. These are very powerful techniques, and as we noted yesterday, the way in which these measurements are done can be in the form of using X-rays as an excitation and the event detected, or, for example, using a connection with electron emission as a way of deducing information about a sample. Okay. But of course, there's other ways of going about atomic scale characterizations. One very powerful methodology, and one that requires some degree of sophistication to perform measurements of this type, due to the fact that the probe particle in this case is a little bit more difficult to come by, namely the use of neutrons. Neutrons are, again, a very small low mass particle which possess very short wavelengths. Wavelengths that would be characterized by the energy of the neutron that's being used. And typically, these wavelengths would be of the order of an angstrom or thereabouts, again, making them appropriate for the characterization of interatomic bonding. Neutrons also carry with them the ability to do distinctions of atomic characteristics in ways that are actually fairly powerful. For example, isotopic labeling provides a really powerful way to understand the bonding habits and organizational states associated with hydrogen atoms that may be present in a structure. And this is frequently done by using isotopic labeling as a way to provide contrast. The scattering cross sections are different for those two nuclei, and that actually gives a way to do very high resolution speciations and characterizations, even in cases that would normally be very, very, very difficult. Now, of course, because neutrons are a particle that's typically found in the nucleus of an atom, you tend to need things like a nuclear reactor or a very high energy accelerator in order to gain access to them as a probe, and these are typically done at large government laboratories where such facilities would be available. And finally, and probably one of the most scalable and empowering methods of doing atomic scale characterization is via the use of electrons as a probe. Electrons, again, are low mass particles which can be accelerated to very high velocities, giving them a tunable and basically a capability for extremely short wavelengths. So in principle, at 200,000 electron volts, an electron has a wavelength that's massively short compared to interatomic bond distances. And in principle, this allows one to do direct observations of atomic positions. In practice, though, the presence of non-idealities in the microscope make the working resolutions less than what the theoretical possibilities would be. So rather than 2.5 picometers, it might be something less than that, but still very easily brought to within limits that are greater than brought to limits that make it directly possible to do atomic scale characterization via direct imaging. The other thing we should note is that the scattering events in this case are not like X-rays. X-rays see the electric field associated with the electrons, and electrons in this case being used as a probe more or less see the Coulombic fields associated with the nuclear charge. And we see on the slide an example of scattering events determined by where the electron trajectory is relative to the shell structure of in a schematic form of an atom. And that basically, for trajectories that come close to the nucleus, we have deflections at large angles. This is the equivalent of Rutherford scattering, but rather than using positively charged particles, this is a negatively charged particle interacting with a positively charged core. And we see that that sort of scattering would actually change the nature of a propagating electron beam in a way that would render that scattering event detectable, and hence atomic positions in principle detectable. We also saw yesterday cases in which the interactions of electrons with the electron system of an atom also give rise to excitation. So, for example, the loss of an electron from a bound state in the atom, right? And that excitation, an ionization event, then gives rise to subsequent outcomes. For example, we get photoelectrons that we can detect, or we get X-ray emission. And again, these secondary processes also provide a capability for doing characterization with transmission electron microscopy that would allow us to deduce things not just in terms of atomic positions, but also chemical identities. And we'll explore these ideas in a little bit more detail. So, for example, via electron energy loss spectroscopy or X-ray emission, we can actually do fairly important and useful forms of characterization of electronic structure and chemical composition and bonding states directly in the electron microscope. Now, I've been saying in the last few slides that we're going to be speaking about transmission electron microscopy, and it differs from scanning electron microscopy as discussed yesterday in that we're not looking for the information content of electrons that scatter back off of the surface of a sample. In this particular case, electrons have to actually penetrate and pass through the material because they're detected after they pass through the material that you're interested in characterizing. In this sense, then, because of the fact, as we've mentioned many times, that electrons interact very strongly with matter, your samples have to be very thin. So electrons have the advantages that they're very easily generated. They provide mechanisms for deducing chemical bonding information, so they're chemically sensitive. In a very important sense, the way in which the optics work, electron optics work, they're amenable to very high-level forms of design and great sophistication, and it's actually a fairly well understood area of science now. So, in principle, they have really very advanced lens designs that empower modern microscopes. And also there's been significant advances made in detectors, which make it possible to minimize the amount of electron beam exposure that's needed to deduce measurable signals. And these have a lot of advantages, in terms of like how practical forms of atomic resolution imaging can be brought into your analytical laboratory. So what's the nature of a lens system that's used for an electron microscope, and in particular for a high resolution electron microscope? Well, basically, we like to use the analogy of a lens, that we have light passing through a lens, and, we have a curvature and a different path length, et cetera. We apply, the laws of optics to this, and we can bend, parallel trajectories to get convergent beams or divergent beams. And that's a nice analogy, but in point of fact, there is no transmission lens made of a solid substance that works for an electron, right? And that really means that the lens systems are actually electromagnetic coils that are used to generate magnetic fields and electric fields that are used to change the trajectories of electrons in ways that mimic the characteristics associated with a lens. Okay. So what does a modern high-resolution transmission electron microscope look like? Basically, it looks like a very large cylinder with lots of wires and things hanging off of it, and much like what we saw yesterday, except this is somewhat obviously larger in scale and vastly more complicated. So this is the column of a particular microscope that actually contains a number of very advanced components that make it possible to do atomic resolution imaging. So it's a very high quality electron gun that's basically up here at the top, a number of lens systems, places where the samples come in, detectors that allow energy discrimination, and finally detectors that allow you to do the collection of an image as well. And that's shown here schematically in terms of what the layout of components are. And basically what you see is the following, right? There's a place where we generate the electron beam. There's things that are used to form that beam. There's things that are used to actually provide one level of magnification. There's things that are used to provide another level of magnification. And finally, we get to a place where there's things that exist to provide another level of magnification. So this is actually a compound microscope in which each lens element adds some level of magnification that all operate progressively to allow you to approach magnifications that approach atomic dimensions, or actually currently, that are at or exceed atomic resolution. Right, so there's not one lens that does this. There's many lenses, and that's actually a fairly important thing. And the other aspect is where is the sample relative to the lens systems? And so, for example, you'll notice there's a label here that says objective lens, and there's another label here that says objective lens, and that actually turns out to be important to determine whether or not a microscope is operating as a transmission electron microscope or a scanning transmission electron microscope, and we'll illustrate what those differences are in the next few slides. So electron sources for these kinds of instruments. At the limit of atomic resolution, you're going to have to really be working with a microscope that has a field emission source, and those are really quite powerful electron sources that deliver high current densities, and actually they're reasonably robust, but rigorously requires that the column operate at ultra high vacuum conditions. And in more routine analytical instruments might, for example, use an emitter source that's based on a tungsten wire. And now imaging, classically imaging, so you're all probably young enough that you don't remember television sets the way I do, okay? But you probably think the world always had flat panel displays, etc. No, it didn't. In the old days, we had phosphor screens, and when electrons hit a phosphor screen, you get a light emission, and actually that's still a powerful way of doing imaging, is to have electrons hit a phosphor, and you just take a picture of the light irradiance that comes from electron phosphor induced emission. And but more modern approaches are actually to use an electronic detector, a charge coupled device that the electrons impacting generate a recordable signal in a pixel array, and that data can be read out of the array in the form of of the information that a grayscale contrast image can be constructed from. And these detectors are actually, very empowering in the sense that they make it possible to do very fast measurements, and also provide a capacity to allow the beam fluxes to be minimized to a level where the impacts of radiation damage can be mitigated. Okay. So let's think about how we would describe the hierarchy of excitation or the probe event, and all the things that we can do subsequent to that, that would provide us some understanding of the structure of a material. So we have an electron beam, and this will be a high energy electron beam. Like for example, several hundred thousands or several tens of thousands of electron volts. And those accelerating voltages are needed to provide electrons with very short wavelengths. We might choose different values of these accelerating voltages from the perspective of mitigating the consequences of beam damage. There would be a difference, for example, with regard to a microscope operating at 90,000 electron volts or 300,000 electron volts. But obviously, very high accelerating voltages would make it possible to look at thicker samples than would be possible with thinner samples. The specimens must be very thin because most of the interest is in looking at the electrons that actually come through the sample. Okay. We might, in fact, do other kinds of measurements as well. So, for example, we saw yesterday electrons coming back the other way. Auger electrons would be one characteristic form of data. We might actually do X-ray detection, the X-ray fluorescence events. And we talked about this in the context of scanning electron microscopy yesterday. But in this case, we're really going to think about what happens when we have fine probe electron beams, such as shown here, and we can actually then begin to look at electrons that are transmitted more or less in the direction of propagation of the beam. We can look at electrons that scatter but are still transmitted, and scattering elastically, that actually are those are actually electrons that have experienced a diffraction condition. All right, so we can get information about atomic positions via diffraction events. We can also look at transmitted electrons that lose energy, and that actually provides a spectroscopic capacity about specific bonding states and chemical identities that are present in the material. Okay, so let's go ahead and look at this in further detail and think about like how it is that we actually get electrons through a sample. Well, making samples for electron microscopy of this form really has a little bit of art associated with it. If you're working with nanoscale materials, it's frequently appropriate just to take bits of your sample and disperse it on a grid. All right, and there's a picture here of grids, and the most useful form of grids. So here you can see the dense metal component of this grid, and actually what's present here is an extremely thin coating of material. And various materials are used. One common one is so-called silicon monoxide, SiO. Carbon, though, is actually one of the preferred grid spanning materials. And the reason for using this is that carbon is relatively low Z, right? It has low atomic number. And the contrasts in electron microscopy come from basically the sizes of the atomic number of the atoms that are present. So very thin films of carbon actually have very low background, and hence, if we're for many of the samples we're looking at, that would be basically a substrate for holding them that would contribute very little to the image. So that's actually a very powerful way of preparing a sample. But there's other ways that can be used as well. So for example, ion milling and also the use of focused ion beam fabrication tools finds extensive use as modalities for preparing samples for this kind of microscopy. Okay. For those people who work with soft materials, and it's actually also probably evident to you that one of the more powerful impacts in the development of understandings of biology came from electron microscopy, and one of the really wonderful things that was done was basically the development of thin film preparation methods for biological matter, but also all the stains that were developed to provide enhanced contrast for these kinds of samples. And on this slide, you see an example in cartoon form of how a thin film section, so this is actually a thin film section of cellular content taken from the liver of a rat after fixation, and obviously staining is done to this as well. But basically what happens is that cells are embedded in a resin. It could be either an acrylic or epoxy. There's a variety of different polymeric types. When it's set, you then actually take a very sharp blade, and this could be, for example, a diamond blade, and we call this a microtome. And you section off a very thin piece, and if you do this very carefully, you then pick that very thin sliver up on a grid, you can then go ahead and actually do a transmission electron measurement on that very thin sample. I have never succeeded at preparing samples this way with any kind of quality at all, and the people that do it are remarkable. But you can see that you can develop, really, beautiful substrates for doing measurements with this kind of approach. Okay. Now let's talk about modes of imaging, and people will use different terms to describe the form of imaging that they're doing, and the two common ones you'll hear is bright field and dark field imaging. Here's an example of a bright field image, and basically what this is that we have a beam of electrons that goes through the sample, and basically what we do is we look at the electrons that are transmitted through the sample along the axis of its propagation. And this is actually the most common imaging mode for most forms of electron microscopy. And in the image that you see over here, what you see are pictures of a labeled organism, a bacterium, and it's been labeled with gold clusters, right, which are bound to a specific a target, and you can see little black dots that are basically all over this structure, right? And the little black dots are actually the gold clusters. And what you're seeing in the image is contrasts that relate to the density of parts that are present. the very small gold clusters being small but high Z look dark, and things that look dark are dense, and things that look bright are much less so. This is actually a very good way of imaging things, but typically we're looking at larger scale structures of the order of tens of nanometers. And one of the things that's very important is that one can get fringes that lead to degradation of the images, and these are sort of well-known artifacts. In skilled hands, you can actually mitigate those effects. So I guess the thing to be aware of is that if you see scales of structure that are typically hard to see within a particular form of imaging, they're probably not real. Okay. All right. But now let's think about other ways that we might be able to use a bright field imaging protocol, but do this in a way that that actually provides an enhanced form of information recovery. And here we have to actually think about where it is that the sample sits with respect to the objective lens, okay? And the thing that we have to do is we have to do this from the perspective of thinking about that earlier slide that showed the multi-lens system of the microscope. And note that I said, either above or below the objective lens is the place where the specimen sits. And here we see that in bright field imaging. In point of fact, the operating objective lens actually sits below the specimen. All right, and so the form of normal bright field imaging that we saw, we have parallel beam of electrons that penetrates the sample. Even if we have diffraction contents, we can look at the 0-0 beam of this interaction. Take that, pass it through an aperture after it's brought to a focus at this aperture, and we notice that if we were to actually look at the intensity patterns that are present at that aperture plane, that actually corresponds to a diffraction pattern, right? And that we can then look at the transmitted beam, that's the normal bright field image. But in point of fact, we can actually select points in this diffraction pattern, move the aperture with respect to those places, and look at the electrons that correspond to a specific diffraction order in the sample. And when you do that, you see things such as the following. These are examples of gold clusters grown on sodium chloride. And you'll notice that in the bright field image, they basically, and you can see like little shapes in here, these are like in this projection here, and that's actually an important point. I should say something about what's true about electron microscopy. Atoms are present in three-dimensional arrangements, okay? But when we're looking at an electron micrograph in transmission mode forms of measurement, it's a projection of everything, right? We're looking at a 2D projection of a three-dimensional object, and that actually generates some difficulty in actually understanding, what it is that we're seeing in a particular image. So I know, something about the projection of particle shape, but I don't necessarily know, what that particle actually looks like in 3 dimensions. But some understanding can actually be elicited just by looking at how optically dense it is, right? Because in essence, if a part of a sample is brighter and part of it's darker, well, there's got to be a scaling of density, right, in that axis of projection, right? But having said that, we notice that, for example, some things look sort of like almost hexagonal, some things we find things that look square, and obviously there's different crystallographic polymorphic conditions that are being evidenced here, and we can look at diffraction orders and pick one, and then actually look to see what the image looks like by taking those electrons and constructing the image. And basically what you see in this case are only specific diffraction related conditions that say, what is being looked at, right? And so, the things that appear bright in this case are actually crystals that project a zone axis that has the correct orientation to be an electron seen at that diffraction point, okay? And that's the image that we get, are for only those crystallite habits that correspond to that diffraction condition. And so that actually is another way of providing contrast in this sort of normal mode of TEM imaging. Okay, so another way that we can actually do high resolution imaging is actually to collect all the diffraction orders that are generated by an interaction of a specimen with the electron beam. And here we see, a cartoon version of different diffraction orders being organized by the interaction with the objective lens, and actually all brought to bear at focal points, right, at the image plane. And that actually provides a capacity to do atomic resolution imaging when in fact the orientation of atoms provides a capacity to do projections through the sample and actually visualize, right, the atomic columns that are present, right? And so so basically, this is sort of an advancement, an enhancement that comes from the details of the lens design that are used. And you'll notice that, what we can see here are, the ordered columns of atoms. And we don't really know anything about, like what it actually looks like that we're looking at. It's just that we can see that, there's an alignment of the columns of atoms, and we can see places where columns of atoms are and where they are not. But also what you can notice in this image is there's actually, something that looks like, there's a column of atoms that might be here, or a remnant or something like that. And that's actually a fringe, associated with, basically an artifact associated with this form of imaging, right? But you can see that this is really beginning to approach, something that's at atomic level understandings of the structure of this gold particle. And clearly, looking at this, you would say that this small nanoscale cluster, a few nanometers in size, is actually a single crystal, right? And that really is a quite beautiful image. It's a 1 nanometer scale bar, so that's fairly challenging imaging condition. Okay, the thing that's beautiful about this class of measurement is that we have the capacity for bright field and dark field measurement. We also have the ability to look at diffraction contrasts, and the thing that I think is important to think about is, like, what kind of imaging mode would you think about using, and within normal TEM or just standard TEM measurements, that's usually a fairly straightforward set of determinations. We might have a thin film sample, we have stains, and we do bright field imaging, and as you can see in this biological sample, you can see where the gold clusters are localized. And actually, this kind of measurement was used very powerfully to look at dynamics in cells as a way of finding, for example, how things are brought into the cell, how they're trafficked within it, and then how they're then ejected out again. You're just using gold clusters labeled with molecules that would target particular receptors. And if you make lots of microtome samples and you do it very carefully and you have enormous patience, you can actually figure out how really important cellular processes work just by looking at where the bits and pieces of label go. Okay, and you can do similar measurements in bright field and dark field mode, depending upon what actually provides a better image contrast for the dynamics you're trying to understand. Okay. So anyway, so this is actually a fairly powerful way of doing things. And what's actually nice about the contrast is that if you have hard time seeing a bright object or a dark object against a dark background, or a bright object against a bright background, then we could use, like, for example, diffraction contrast as a way of improving the image contrast. But there's also, like, this notion of, like, what can we begin to do if we actually change the imaging conditions and go not to a standard transmission mode measurement, but to a scanning transmission mode measurement. Okay. And that actually requires us to think about what would be different. And this is actually, the important difference. In STEM mode, the placement of the objective lens is different, right? Rather than using an objective lens that's below the sample, the objective lens is actually placed above the sample, okay? And the reason why this turns out to be important is that it provides a capacity to generate a beam that actually has a very fine probe dimension, right? And what we would do then, in this particular case, is to use this very fine probe beam as a way of doing a point-by-point interrogation of the transmission properties of electrons through the sample, right? And actually, the other part is that we use the electron atom interaction as a way of acquiring an image, right, which comes from Z contrast associated with electrons interacting with nuclear charge and being deflected at large angles. So that's actually shown here in this cartoon as electron trajectories that are impacting an annular detector having scattered at a large solid angle. Okay. So what we would do is we would raster this beam across the sample in a sequence of XY coordinates and reading current, right, at this detector associated with each position of the sample. And in principle, this probe beam can be brought to dimensions of the order of atomic resolution, and hence anything that I read here in terms of current to this annular detector corresponds to contrast information at atomic dimensions at that position of the beam. Okay. So let's think about how we might look at this from the perspective of samples, right? And that is what's the limit of the of resolution, and when we're fairly big, all right, in terms of, and fairly big in this case being, we're going to do resolution like of the order of a few nanometers. You actually can use TEM and STEM mode measurements in this context, and then when things start to become really small, and down to atomic resolution, STEM mode measurements, really become the most empowering form of electron microscopy that you could do. And the other part is that if we couple this to other forms of measurement, for example, EELS measurements or X-ray emission measurements for chemical speciation, having small probe sizes is also quite empowering. So we can do X-ray measurements, and now we don't have an excitation volume because the sample's very thin, and we have an atomic resolution probe. We can basically do X-ray measurements that are very proximate to an extremely small probe diameter, right? And so that actually becomes a way of doing nanoscale measurements of chemical composition. Okay. Now, the X-rays, even in this form of measurement, are exactly the same as what we saw before, and that is, they arise from ionization events and relaxation events that lead to X-ray fluorescence. And even though this is a small-scale generation event, narrow volume elements being excited, the underlying dynamics in terms of how the electronic structure of the atom is involved are exactly the same, right? There's no differences. Just the scale of the event that's generating the X-ray flux. Now let's talk some more about the issue of diffraction. Typically, diffraction is something that tells us about the ordered components of a sample, and we have electrons that elastically scatter off of the atomic structure of the sample, and we can look at the diffraction patterns and understand those diffraction patterns in terms of characteristic spacings of crystallographic planes, and from that we can deduce information about the structure of a solid. Actually turns out with fine probe beams and diffraction done at very small scales, we can actually, in particular using coherent probe beams, you can use that diffraction image, and this is really at the state of the art, to acquire information about atomic structure directly by inverting the diffraction pattern in a computational form. By recovering the phase information within it and actually directly determining the structure of a solid. So there's two examples here, and you can see at the bottom of the slide the references for that. And I would commend you to go and look at this. I just call out this one example here, which is spectacular. This is one of the early examples of this kind of coherent imaging. Where this is a diffraction pattern, and what's recovered from this is the atomic structure of a double-walled carbon nanotube, and the components here that you're seeing called out actually show what the local helicity, chirality, and overlay of the hexagonal meshes of the two carbon nanotubes are, right? And you can actually see, like for example, this is the theoretical depiction. This is actually the recovered image that shows what this double-walled structure corresponds to. I mean, this is really spectacular, and you can see that for example, the structural elements embedded in here are at the level of 1 angstrom in terms of the resolution. Spectacular. It's really amazing. Okay, so diffraction is actually a pretty empowering form of measurement, and but frequently when we're doing atomic resolution imaging, so here's actually two examples of atomic resolution imaging that's done on a particular sample. These are palladium nanoparticles supported on, I believe, a carbon substrate. This is one of my students' samples, and I've actually forgotten what the substrate is, but I believe it's on carbon, but it could be silica as well. But anyway, you can see in both of these images, atomic resolution imaging is being done, except that it seems like one is just a little bit poorer in terms of the focus on the sample. Well, when we do diffraction, diffraction is a case where the atomic positions of the sample actually act as the grading, right? That gives us the orders of diffraction that are seen as spots. Okay, and that really is a fundamental measurement that's elicited via the periodicity, right, in the long-range translational order that's present in the sample. Now, one can also acquire information that's sort of the same type by actually just doing a Fourier transform of the intensity that one measures in this projected image. And one gets something that looks like a diffraction pattern. That's actually shown here. These are what are referred to as power spectra. Power spectra have sort of the same information as a diffraction pattern. You can get things that are related, like, so for example, Power spectra might allow you to actually determine what zone axis is oriented along the line of sight in the micrograph that you're looking at. So like what crystallographic axis am I looking along when I see the atomic positions that are present, for example, in this cluster that's shown here. And except that power spectra also are probably less powerful than a real diffraction pattern because they actually are impacted by the resolution of the instrument, right? So they can actually give you an incorrect understanding, or at least a less clear understanding of what the atomic ordering might be like. But again, it's a useful form of measurement. But what can we do with electron diffraction in fine probes? Okay, well, here's an example, right? And it's just one example. Here's a bright field image of a single crystal gold nanoparticle. So it's just of the order of a few nanometers in size, right? And you see the atomic resolution imaging. These images can be very fundamentally modeled using computational, theory-based computational tools. And we can understand something about structure by looking at the correspondence between simulation and measurement. But here's actually a more powerful measurement. Here are measurements that are performed using a coherent diffraction protocol, but actually looking at particular diffraction orders and then theoretically calculating what the diffraction condition would be for a finite cluster size and arrangement of atoms, and actually looking at what various forms the models would predict and correlating that with experiment. So that's actually what's shown in this 4x4 grid of real data and theoretical simulations. And the important point that's actually established here is to not only understand where the atomic positions are, but to understand what the kinds of structural complexity that's also embedded in the object. Because here what we're going to actually do is not just look at a two-dimensional projection, but actually wrap that up in a three-dimensional model of the atomic positions, and also allow the atoms to relax from their theoretical bulk-like bonding positions. And the reason why you would do this is because crystals that have finite truncation planes actually have peculiar forms of structure in it. So, we have atoms that are present on terraces, and they might be 111, 100, etc. And we have edge planes, we have vertices, and basically the atoms that are present in all these different places relax from idealized atomic positions. And actually this data allows you to determine that. So one can look at this and one finds that bonds are strained of the order of a few percent of the of what would be an unrelaxed bond distance, and that actually turns out to be a really large energetic impact on the thermodynamics of the cluster. So these things would have really large consequences, for example, in things such as catalytic properties. Okay, another form of spectroscopic measurement is just to look at not just the elastically scattered electrons, but also the inelastically scattered electrons. And we can think about like what are the energy loss mechanisms, and the scattering angles. So the ones that become more easily detectable are the ones that correspond to large energy loss. A few electron volts, to 1,000 electron volts. Those actually are ones that are related to the core. The electronic states of deeply bound states of atoms, right? By the time we're at 1,000 electron volts or something like that, and milli electron volt energies are at the level of vibrations. And Measurements can be done across the scale, but not all of them are practical. But actually, some of the more interesting ones are ones that are at energies that are of the order of bound states of electron in the sample, and that actually then begins to be a measurement related to electronic properties. And I'll go through this slide quickly, but just to say, like, here's an atomic resolution image of a multi-layer stack: strontium, titanium oxide, strontium manganese oxide, and this is a fairly complex oxide material, and in which there's modulations of strontium, titanium, and manganese, and one notices in this that we can actually look at the Eel spectra associated with the placements of atoms, like, for example, particular levels for titanium, manganese, and lanthanum, and also oxygen, that tells us about how substitutions of atom types lead to changes in electronic structure of all the atoms that are bound in that crystal. So this is the kind of measurement of and the kinds of details that can come from atomic resolution imaging of this type. Now, last thing I want to mention before we get into the more direct applications of atomic resolution imaging is how do we think about the issues associated with the fact that we're looking at a two-dimensional projection of what are intrinsically three-dimensional objects, and some really beautiful things can be done if you have really sophisticated capacities for both measurement and manipulating samples. So many of you know the term tomography, right? And tomography is one way of recovering the full three-dimensional information by actually doing a series of projections, but in which the projection is at samples the different angles through the sample, and then we can mathematically reconstruct what the full three-dimensional projection might be, right? And there's a cartoon version that looks as taking an object and looking at it in various projections, and then you can take all these projections and recover, right, the full three-dimensional shape of the object. These are one of Paul Alivisatos' tetrapod nanocrystals, right, which have a core where the growth nucleates and then grows arms out, and there's actually a phase change, right, at the juncture where those rods grow out of the crystal, and you can actually get that three-dimensional shape, which is illustrated in this slide, but with the proviso that you can do a series of measurements. That you can do a series of measurements in which you can also rotate, right, the sample, but without changing the point where the beam is touching it, right? So you have to be able to rotate, within the volume element of the sample. And obviously, when things are very small, that's actually very hard to do. And but with good instrumental design, it can be done. Measurements can also be done in environmental context. Now, this is going to be a hard-to-see movie, but it's a great one. And what's being done in this particular case, if you look at this, you'll see little things swimming around, and it will grow progressively darker, and the dark things will actually start to become bigger. You'll see, like, for example, right here, one of the dark things becomes a little bit, now they're coarsening and becoming bigger. This is actually a nanoscale imaging that's being done in aqueous solution. This is a thin film cell, and the electrons are actually being placed through a liquid volume element that's sandwiched between two very thin membranes, and you actually can see the growth of an ensemble of clusters. It sort of looks like it's trying to go to hexagonal symmetry. These are gold clusters of like, say, nanometer. So that's a 5 nanometer scale bar. So these are like 5 nanometer clusters, And you can see, starting to arrange themselves with hexagonal symmetry around a central core cluster, and actually following that growth pattern and self-organization in real time in a fluid environment. This is really a spectacular measurement, and they were able to use this to understand, how the growth dynamics work. Is it simple growth and growth with coalescence, et cetera. And what's the particles that have to be exchanging between different clusters in order to coarsen and grow larger ensembles. Okay, I'm going to skip this slide because it's a little more detail than I think is useful. I'll also note that one additional thing that's coming into play now as well is the advent of so-called 4D electron microscopy. And that actually is, in fact, normal electron microscopy, right? But also manipulated in the time domain, right? So rather than having a steady beam of electrons, what we have are little pulses of electrons where we can do the event with time resolution that can actually become, go into the pico to femtosecond time scale, right? And that actually is shown here, high temporal and spatial resolution. So if you follow the set of figures here, this is a laser pulse that's being used to explode a crystal. And the imaging that's being done is to actually follow, how that event rips all the atoms apart, and so this is actually, I think, going to be one of these up and coming forms of measurement that we can actually follow, atomistic dynamics in real time and high spatial resolution, directly in an electron microscope. Okay. All right, so where do we go from here? And I've started alluded to this notion that the microscopes are becoming more capable, and I just want to close by noting some of the things that have happened very recently that really have I think totally changed the game of what's doable, and that is the ability to treat and remove aberrations that fundamentally limit the resolution of electron microscopes. We have electrons that have fantastically short wavelengths, but microscopes that don't realize the full precision of that short wavelength. And aberrations are at the heart of what limits this. And so and just using the analogy with light. So here's an uncorrected lens system for using light, and we notice that. One of the most important forms of aberration are spherical aberration, and that is, light photons that pass through the edge of a lens and photons that pass through the center of the lens are not brought to the same focal point. And it actually takes a compound lens system to change this condition such that no matter where the parallel beam strikes the first lens element, they're all brought to this common focal point. And we would have to have the ability to do this, for example, for an electron microscope that would work, with any form of measurement, right? So, for example, whether the specimen plane is above or below the objective lens, and in point of fact, this problem has been solved. And so this is just an example looking at the coherence, right, of an electron beam this is at a detector, and by actually incorporating a higher order multi-probe lens element to correct spherical aberration, right? And this is called a CS corrector, which allows us to generate actually a coherent and aberration-free central component, right, of this propagating electron beam, and an exact analogy for what we saw for the light case. Okay, so what can we do with that? Now, all of a sudden, when we start looking at the atomic positions of atoms present in the cluster, they just jump out at you, right? I mean, it's like you've acquired the ability to see atoms. And if you look really carefully at this micrograph, okay, and I don't know if how visible this is from where you're sitting. There's little blue dots all over the place, and the way I like to say this is once you acquire the ability to see atoms, you find out they're everywhere, and so these are platinum atoms. And for a very small cluster. Actually, no, I'm sorry. These are palladium atoms. No, these are platinum atoms. These are palladium atoms down here. This is actually a cluster that's a really peculiar one. It looks like it's like not really all that well defined. But actually, if you do theoretical models of this cluster, it's actually got not the structure of the bulk metal, which is face-centered cubic. This is actually a small cluster which is grown with an icosahedral crystalline form. And that's actually a theoretical model that actually illustrates the specific orientation of that icosahedron. We can actually go through and deeply analyze complex speciations. And so, for example, when you get multimetallic cases, because this measurement has Z contrast, you can tell what atoms are which based on the kind of image contrast that they contribute. So let me go one ahead, and I'll show you an example of a binary cluster that's formed from platinum and palladium atoms. And what you notice is that some of the places appear bright and some of the places appear dark. And that's actually because of the fact that we're looking at the ordered columns of atoms, but in which platinum and palladium are phase segregated within the cluster. And you can actually calibrate those intensities and count all the atoms that are present in the cluster. So now we can go ahead and not only say, this cluster is oriented along a certain direction, but we can also define all the truncation planes of the crystal, tell you where the particular atom types are, and also tell you the numbers of atoms of each type that are present within the cluster. And so palladium and platinum are sufficiently different that it's easy to distinguish them by this Z contrast form. Okay, this is all done via high angular dark field imaging. So that's using that Rutherford scattering condition that we talked about earlier. And you can just, the more crystal, the thing is, the more crystals you have, the more data you can acquire. And we can take slices from it and look at, details of structure. For example, this particular slice, we can count all the atom types that are present and actually deduce, how many atoms are present in each projection along that axis. So now we're really looking at three-dimensional information. And people have taken this to incredible depths. So for example, it's a boron nitride thin film, but containing different amounts of carbon and oxygen impurities. And so for example, you can look at an image, like there's the raw image, and actually find places where there's misplaced atoms of a different compositional form. Not everything is boron and nitrogen. Some of the things are actually oxygen and carbon. And this image of this monatomic plane of atoms is actually showing that speciation difference just based on differences in the atomic number of the atoms involved. Okay, and finally, I'll note one last thing, that with very fine probe beams and high energy resolution, which is another aspect that comes into play with this class of matter, we can also look at, in this particular case, these are gold clusters supported on TiO2. For those of you who study catalysis, this is a very interesting catalyst where gold becomes active when it's really small, but on an active support. And the properties are related to charge exchange characteristics associated with the metal support interactions. It's my theory. It's not agreed upon in the literature. Okay, but anyway, you can do measurements of electronic structure using EELS-based measurements and actually find differences, at that boundary or off that boundary that correspond to the metal clusters sitting on sites that look like not titanium-4 but titanium-3, right? That there's oxygen atom vacancies that are present that modify the electronic structure at the point of juncture between the small particle and the support. So this is like a really fantastic level of information. So what's the key points? We can basically do measurements of chemical speciation, atomic structure, dynamical properties with atomic resolution, and really, this is advancing rapidly. But the real interesting point is it requires a sense of imagination and wonder to go ahead and tackle these really terrific instruments and bend them to your will in the context of an experiment that might matter. So at that point, I'd like to thank you, and we'll end this lecture at this point. Thanks.